public key infrastructure quietly underpins many of your most critical services: authentication, encryption, and data integrity. When PKI is healthy, everything just works, so it's easy to forget how much risk is concentrated there. The real danger is that PKI usually doesn't fail loudly at first. Small gaps in certificate management, weak revocation processes, or uncontrolled shadow keys start as invisible weaknesses and only show up later as outages, broken trust chains, or exploitable security holes. In this module, we'll treat PKI not as a static technology, but as an operational system that can degrade over time. We'll look at where it typically breaks, how those failures impact business services, and what controls you need to keep trust reliable at scale. Certificates are not permanent security assets. They're perishable. Each one has a fixed start date and a hard expiry date, and when that window closes, trust collapses instantly. In practice, a missed renewal can break TLS handshakes, take down APIs, or lock users out of critical services, even though nothing else has changed. Now layer in complexity. Multiple CAs, different certificate types, several clouds, and teams issuing certs independently. The number of moving parts explodes, but the expiry clocks keep ticking at the same unforgiving pace. The real risk lives in the governance gap between expiry and renewal. If no one owns that gap, certificates lapse silently, or get replaced in a rush with weak processes and poor visibility. Modern PKI success is less about can we issue certificates and more about can we continuously manage their life cycles without outages or blind spots. In modern environments, a single certificate is rarely just a certificate. Think of it as a tiny root of trust that many other systems quietly rely on. When that trust anchor fails, most commonly because it expires, the impact rarely stays local. The first visible symptom might be something small, like an internal API refusing connections, or a monitoring tool that suddenly can't talk to its agents. But those APIs often sit in the critical path for logins, payments, deployments, or observability. As they fail, more services start timing out, retrying, and backing up. Load increases, error rates spike, and suddenly you're dealing with a major incident that looks like a generic platform outage, even though the root cause is a single expired certificate. This is why PKI isn't just a cryptography topic. It's an availability and business risk topic. One unmanaged certificate can escalate into customer visible downtime, almost SLA breaches, and direct revenue loss. Certificate expiry problems almost never start as a crypto issue. They start as a people and process issue. When no one has a complete inventory of certificates, teams simply don't know what exists, where it lives, or when it expires. Add unclear ownership, and alerts end up in shared mailboxes that nobody truly feels responsible for. Manual processes make it worse. Spreadsheets, ad hoc renewals, and change tickets all create opportunities for human error or simple procrastination. Then there are blind spots, internal APIs, legacy systems, IoT devices that never made it into any catalog. All of these factors converge on the same business outcome: unexpected outages and service disruptions that were entirely predictable, but not governed. Once you start deploying PKI at scale, the first real challenge isn't crypto, it's visibility. You can't protect what you don't know you have. You want every certificate to show up like a blip on a radar: which CA issued it, which domain or service it protects, who owns it, and when it expires. That calls for a single centralized inventory, instead of every team tracking certificates in their own spreadsheets or ticket queues. Inventory on its own isn't enough, though. You also need active discovery that continuously scans networks, DNS, cloud accounts, and endpoints to uncover unknown or shadow certificates created outside your formal processes. These are often the ones that expire unexpectedly or use weak configurations. Once you can see everything, you turn that awareness into action. Integrate certificate data with monitoring and ticketing systems, so upcoming expiries, misconfigurations, or policy violations automatically generate alerts and work items. This combination of inventory, discovery, and automated response becomes your first line of defense against outages and trust failures. And it's the operational foundation for any serious PKI strategy. Now that we've looked at visibility, the next challenge is scale. With manual certificate management, every step needs a human. Requesting, approving, installing, and renewing. That means tickets, spreadsheets, and calendar reminders. It's slow. It doesn't scale. And eventually someone misses a renewal date, potentially taking critical services offline. Modern PKI design replaces these touchpoints with automation. Using APIs like ACME or simple REST calls, systems can request and renew certificates themselves, with zero human interaction in the happy path. That also enables short-lived certificates, which reduce risk because a compromised key naturally expires quickly. To make this reliable, automation has to be introduced with discipline. Dedicated test environments, staged rollouts, and clear rollback plans. Done well, automation doesn't just make PKI faster. It makes your overall infrastructure more reliable, because you're no longer depending on humans to remember thousands of tiny cryptographic deadlines. Revocation is supposed to be the kill switch of PKI. When a private key is stolen or a certificate is misissued, revocation is how you tell the world, don't trust this anymore. In practice, that kill switch is fragile. It depends on two mechanisms: revocation lists that have to be published and downloaded, and an online protocol that has to be reachable in real time. If those lists are stale, a certificate that should be dead can still look perfectly valid to browsers, apps, or devices. If the online check is down or slow, e-consor systems face a bad choice: block users and cause an outage, or quietly skip the check and accept potentially dangerous certificates. So the paradox is that revocation exists to protect trust, but when it's unreliable, it can either break availability or silently weaken security. Modern PKI design has to treat revocation not as a checkbox feature, but as a critical high-reliability service in its own right. Revocation is meant to be PKI's safety net, but when it's handled poorly, it creates a very dangerous illusion of trust. If revocation data is stale, a certificate that's been compromised, or should no longer be used, can still be accepted for hours or even days. From an attacker's point of view, that's free time to impersonate services, decrypt traffic, or maintain access. On the other side, if your OCSP or revocation service goes down, clients often have to choose: block the connection and break availability, or soft fail and let the connection through. Under pressure to keep systems running, many organizations configure clients to ignore revocation failures altogether. The result is that you think you have revocation controls in place, but in practice, they're rarely enforced. In a zero-trust environment, this is critical. You must assume certificates can be stolen, and design revocation to be timely, highly available, and actually honored by clients, or the entire trust model weakens. When a system checks certificate revocation, there's a critical decision to make. What happens if the revocation service can't be reached? A soft fail approach says, prioritize availability. If the OCSP or CRL server is down or blocked, the connection is allowed anyway. Users stay happy. Sites stay up. But an attacker with a revoked certificate might still get through. This is why the public web mostly prefers soft fail. Outages are visible and painful. A hard fail approach says, prioritize security. If revocation can't be confirmed, the connection is blocked. That stops attackers who rely on broken revocation, but you're now vulnerable to self-inflicted denial of service. A revocation outage can suddenly take critical systems offline. The key is to align this choice with risk. Public consumer traffic usually leans soft fail. High security internal systems, admin portals, and critical APIs are where hard fail is often worth the availability risk.
Revocation only protects you if it's fast, reliable, and always available. If a browser can't reach your revocation service, it will often assume the certificate is fine, which defeats the purpose of revocation. Architecturally, you harden this in 3 ways. First, resilience. Run multiple CRL and OCSP endpoints. Hide them behind load balancers, and front them with CDNs. That way, a traffic spike, a regional outage, or a DDoS attack doesn't silently turn off your revocation. Second, optimization. Keep your CRLs as small as possible, and use Delta CRLs for frequent updates. That reduces bandwidth, speeds up downloads, and makes it realistic to update revocation data, often, instead of occasionally. Third, client-side efficiency. Use OCSP stapling so the server fetches and staples a fresh OCSP response into the TLS handshake. With must staple, clients can insist on seeing that proof. This removes the need for every client to call your OCSP service in real time, cutting latency and load, while still enforcing revocation. As organizations adopt cloud and DevOps, a quiet problem appears: shadow PKI. These are ad hoc certificate authorities and trust stores that teams spin up themselves so they can move faster, without waiting for central security or infrastructure. From the team's perspective, it feels harmless. They just need TLS for a new service, or MTLS in a test cluster, so they create an internal CA and maybe even hard code its certificate into code or containers. It works, it's quick, and it's completely invisible to the official PKI. The risk is that these mini PKIs become trusted in local environments, but are unknown to the security team. There are no centralized policies, no audit trails, no clear ownership, and usually very weak key protection. When people leave, clusters are rebuilt, or an incident happens, nobody has a complete map of where these SLAs exist or what they've issued. Shadow PKI turns trust from something designed and governed into something accidental. The challenge for modern enterprises is not just building a strong corporate PKI, but preventing this uncontrolled sprawl of parallel trust systems. When we talk about unmanaged trust anchors, we're really talking about certificate authorities that exist outside normal governance. These shadow CAs are dangerous because they silently expand who can issue trusted certificates in your environment. The first risk is zero visibility. If no team has an authoritative inventory of all CAs and routes, you simply don't know what's being trusted, which systems can issue certificates, or who controls them. That makes incident response and forensics almost impossible. The second risk is weak security posture. Shadow CAs often use default settings, outdated algorithms, long-lived certificates, and poorly protected private keys. An attacker who compromises one of these can mint perfectly valid certificates for anything inside your network. The third risk is compliance failure. If you can't prove who issued which certificate, when, and under what policy, you will fail audits. Unverifiable logs and uncontrolled issuance undermine any claims of strong identity or encryption. The key takeaway: unmanaged trust anchors turn PKI from a control into a liability. A mature program treats every trust anchor as a critical asset that must be inventoried, monitored, and governed. Shadow PKI is what happens when certificates, and even entire certificate authorities, appear outside your official PKI program. They often live in load balancers, proxies, cloud services, and DevOps tools that teams spin up quickly and then forget about. The danger is that these hidden roots of trust can issue certificates you don't control, and attackers love abusing that blind spot. The way to regain control is to treat shadow PKI as a discovery and governance problem. Continuously scan your networks and cloud environments specifically for unknown CAs and private keys, not just expired leaf certificates. Inspect high-risk infrastructure like traffic managers, API gateways, and security appliances, where embedded CAs are common. Then add guardrails. Require every CA to be registered. Define who may create them, and block unapproved CAs from trusted stores and templates. When you illuminate these hidden authorities and wrap them in policy, your overall PKI becomes far more predictable and much harder to subvert. At this stage, we're moving from how PKI works to how PKI survives in production. A resilient operational PKI is something you intentionally architect, not something that just grows over time. It rests on 4 pillars. First, a central inventory. You must know every CA, every certificate, and every key in your environment, including cloud and lab systems. Second, automation. Issuance, renewal, and deployment should be API-driven, so humans aren't racing certificate expiry dates. Third, hardened revocation. OCUSP, CRLs, stapling, and high availability need to be designed so you can safely kill a certificate at any time without taking down your business. And fourth, governance. Clear ownership, policies, and audits, so teams can't spin up their own shadow PKI that nobody controls. On top of those, mature programs consolidate ownership, continuously discover unknown certificates, and routinely test failure scenarios, almost like chaos engineering for trust. The outcome is an operational PKI that can handle outages, breaches, and rapid change, without breaking your security or your uptime.